Swayam Prabha. Digital India. Educated India.
Let us look at some examples of solving linear equations using the row echelon form. Here is the first example. Take 2 by 2 matrix 1, 3, 2, 0, and by using elementary row operations, we can convert this into 1, 3, 0, minus 6. Simply multiply first row by 2 and subtract from the second row. Then we get this matrix 1, 3, 0, minus 6. And this is in row echelon form. We can get another row echelon form simply by interchanging first row and the second row, and then use elimination to convert the entry below 2 into a 0. So we get a diagonal matrix, and this is also a row echelon form. So therefore, row echelon form is not uniquely determined from a given matrix. There can be many row echelon forms. It depends on which row operations we use to bring it to a row echelon form. Once I'm given a matrix, I convert this into row echelon form, this 0, 1, 1, 1, and by using the row exchange from first row to second row, and then back substitution gives me this solution. So this is the general method. Given a system of linear equations, we extract the coefficient matrix and make a augmented matrix, and then apply row operations to convert the augmented matrix into row echelon form, and then by back substitution we find all the solutions. Let's look at a non-homogeneous linear system of equations. There are 3 variables and there are 3 equations. It is not clear at this moment whether this system of 3 equations in 3 unknowns has a solution. So let us extract the coefficient matrix and make a augmented matrix. This is the augmented matrix, and we will convert this into row echelon form. So let us look at the first column, and the very first entry in the first column is non-zero, and therefore this becomes a pivot. And using this pivot, we can convert all the entries into zeros by using row operations below 3. So we apply the row operation R2 minus 2 over 3 R1 and R3 minus 2 R1. These 2 row operations gives me this matrix. And this matrix is still not in row echelon form. We have these 2 pivots, 3 and minus 1 over 3, but there is a non-zero entry below minus 1 over 3, and using row operations, I can convert this minus 2 into a 0. So we apply this row operation R3 minus 6 R2, and now we have obtained a row echelon form of the original augmented matrix. Now you see, look at the last row. In the last row, the coefficient matrix has the third row into as a 0 row, but in front of this we have a non-zero entry. Okay, 12 is a non-zero entry, and therefore this system of linear equations has no solution. Okay, this has no solution. So we now don't have to do any back substitution because this system has no solution, and therefore original system also has no solution. Now let's look at a linear system where we have 3 equations in 4 unknowns. Yeah, we have 3 equations in 4 unknowns. It's a non-homogeneous system, and therefore we make a augmented matrix, and we can apply the row operations and convert this augmented matrix into this matrix, where now we find there are 2 pivots. Okay, so there are 2 pivotal variables, x1 and x2, and x3 and x4 are free variables. And also see, the bottom row has only zeros in it. Therefore, this is a consistent system. This is a consistent system, and presence of free variables means there are going to be infinitely many solutions. So we do back substitution to find out all the solutions. So there are 2 pivots. So R is 2. 1 and 2 are the pivotal columns, and non-pivotal columns are 3rd and 4th. Now the non-pivotal columns correspond to free variables, Therefore, there will be two fundamental solutions of homogeneous equation. Okay, so this linear system has a solution, and to find out a particular solution, we simply put free variables equal to 0, x3 and x4 equal to 0, in a prime x equal to b prime. Yeah, then that gives me x2 equal to 1 and x1 equal to 2. X3 and x4 are equal to 0, and therefore 2, 1, 0, 0 is a particular solution of the equation ax equal to b. Okay, now we find out the fundamental solutions of the corresponding homogeneous equation. So there are two pivots and there are four variables, and therefore there are infinitely many solutions. To find these infinitely many solutions, we first construct the fundamental solutions. Okay, so to construct fundamental solution, we look at the non-pivotal variables. The non-pivotal variables are x3 and x4. So we put x3 equal to 1 and x4 equal to 0 and do the back substitution. We find the first fundamental solution. The notation is S3, and this 3 means we are putting x3 equal to 1 and x4 equal to 0. So once I put x3 equal to 1 and x4 equal to 0, then x1 and x2 can be found out by solving the homogeneous equation. I find the second fundamental solution. There are two free variables, so there are two fundamental solutions of homogeneous system. The second one is found by putting x4 equal to 1 and x3 equal to 0. And by doing this, I find s4 equal to minus 1, 4, 0, 1. This is another fundamental solution. And we know that all solutions of the corresponding homogeneous system are linear combinations of S3 and S4. And we add the particular solution of x0 to any arbitrary linear combination of S3 and S4 to get all solutions. Yeah. So x is a column vector, x0 is a column vector, S3, S4 are also column vectors. These two column vectors are equal, and that gives me values of x1, x2, x3, and x4 in terms of these two parameters, alpha 3 and alpha 4. We can substitute any values of alpha 3 and alpha 4 to get infinitely many solutions of the inhomogeneous system of equations. Now let's look at some qualitative aspects of homogeneous system of linear equations. So suppose I have a m by n matrix, and then we consider the linear system Ax equal to 0. Okay. Then it has only the 0 solution if and only if the row echelon form of A has n non-zero rows. So n is the number of rows. Okay, n is the number of rows, and we want to see whether homogeneous system of linear equation has exactly one solution, namely the 0 vector. And that happens when there are exactly n non-zero rows, which means there are n pivots. Okay, there are n pivots. So if there are n pivots, there are no free variables. There are no free variables. So therefore, 0 will be the only solution by the previous theorem. Okay. Now, if 0 is the only solution, we cannot have any free variables, because presence of free variables will imply that there will be infinitely many solutions. But the assumption is that Ax has only the 0 solution. And if there are no free variables, then the number of pivots is number of rows. So the row echelon form will have n non-zero rows. So that's what this proposition says. I'll skip the second proposition. You can read. We will come to a more general form of the second proposition later. Okay. So as I said, the row echelon form is not uniquely determined. So we want to remove this non-uniqueness by putting some more conditions on the row echelon form, and this is done when we define a row canonical form. We impose a few more conditions on a matrix in row echelon form, so that the last matrix that we get using row operations turns out to be a unique matrix. Okay, so suppose I have a m by n matrix, and we say it is in row canonical form or reduced row echelon form. Okay, both the terms are used, depends on who the author is, row canonical form or reduced row echelon form. So this is a matrix which is already in row echelon form, Yeah, but it satisfies a few more conditions. First condition is all pivots must be equal to 1. When we define row echelon form, we did not impose this condition. We simply said that pivots are non-zero, first non-zero entry in the given row. Okay, but now we are insisting that the pivots are equal to 1. The second condition we are imposing on a matrix in row echelon form is that in each pivotal column, all entries above the pivots are also equal to 0. All entries below the pivot are also equal to 0 if the matrix is in row echelon form. But now we are saying that all the entries above a pivot are also equal to 0. Okay. So when these conditions are satisfied, we say a given matrix in row canonical form. Okay. So for example, look at this matrix. Yeah, there are the first column is 0. The second column contains a pivot, and all the entries below the pivot are 0. The third column doesn't have any pivot. The fourth column has a pivot in the second row, and all the entries above this pivot and below this pivot, they are equal to 0. And the next column has a pivot in the third row, and all the entries in that column except the pivot, they are equal to 0. And last column has no pivots in it. So this is a matrix in row echelon form, and the pivots are sliding to the right as we go down from one row to another row. Okay, so this is in row canonical form. Yeah. So suppose we have a matrix A in row canonical form, and suppose it has R non-zero rows. So that means there are R pivots in the matrix. So there are going to be R columns in the matrix where the only non-zero entry is the pivot. All other entries above the pivot and below the pivot, they are equal to 0. So there are such columns. There are n columns. So there are n minus R other columns which don't contain pivots. Now, if suppose R is equal to n, the number of pivots is equal to number of columns. Yeah. Then it has n pivotal columns. Okay. So therefore, all its columns are all its columns are pivotal. So there are only two types of entries in this matrix. Either an entry is 0 or it's a 1. So there are if number of columns is same as number of pivots in the matrix, then all the columns are pivotal columns. Okay. So if A is the identity matrix, if m equal to n, then A will look like this. That we have certain number of pivotal columns. All the columns are pivotal columns. So the matrix looks like this. If m is bigger than n, where I is the so A becomes, if A is in row canonical form, and then if it's a square matrix in row canonical form, if it has n pivots, then it must be identity matrix. If the number of rows is more than number of columns, and every column has a pivot, then A looks like an identity matrix followed by a certain number of 0 rows. So these are the two structures possible for a matrix which is in row canonical form and which has as many pivots as the number of columns. Okay. To transform an n by n matrix to a row canonical form, we first transform it to a row echelon form by elementary row operations of type 1 and 2. Okay. Then we multiply a row containing a pivot p by 1 over p so that this pivot becomes 1. Then we add a suitable non-zero multiple of this row to each preceding row in order to convert all the entries above a pivot into zeros. So these are the new row operations that we have to perform, because pivotal entries are required to be 1 if a matrix is in row canonical form, and all the entries above the pivot must be equal to 0. And so we multiply this row which has a pivot by suitable scalars and subtract the scalar multiples of the pivotal row from the rows above the pivot to convert the entries above the pivot into a 0. Okay. Now one can prove this theorem that every matrix has a unique row canonical form. Okay. I will not discuss the proof. You can read it from the textbooks. Yeah. So unlike row echelon form, which we know that it is not uniquely determined, but row canonical form of a matrix is uniquely determined. Okay. Let's look at some example. Look at this matrix with 4 rows and 6 columns, and we apply elementary row operations and get the matrix in row echelon form. This matrix has 3 pivots, 1, -1, and 6. It is not in row canonical form because the pivots must be 1 for a matrix in row canonical form, and the entries above the pivots and below the pivot, they should be equal to 0. Already it is in row echelon form, so entries below the pivots are equal to 0, but now we want to convert the entries above the pivot into zeros. The method to do that is you start with the last pivot, 6, and multiply this by, first convert this into a 1 by multiplying this row by 1 over 6, and then add suitable multiples of this to the preceding, the second row and the third row. To second row only, first row already has a 0. So you can multiply this row by a suitable scalar to convert -3 into a 0. Then we go to the third column, which has -1. First we will convert this into a 1, and then apply row operation to convert the -2 into a 0. And that will bring this matrix into row canonical form. Okay, so that is the last matrix here, which is in row canonical form. Okay. Now let's discuss inverse of a square matrix. So we define matrix multiplication and many ways of multiplying one matrix with another matrix. Multiplication of matrices in some sense corresponds to the operation of multiplying real numbers. But the property of multiplication of real numbers, which says that if I have a non-zero real number, then there is a multiplicative inverse. This is not true for matrices. Okay, so a non-zero matrix may not have another matrix, so that when we multiply it, then we get identity matrix. Okay, so we define inverse of a square matrix and understand what are the conditions for a square matrix to have an inverse, or we also say the matrix is invertible. So suppose I have a square matrix of size n. We say that A is invertible if there is a matrix B such that AB equal to identity equal to BA. Now this, remember, matrix multiplication is not a commutative operation. So AB equal to I and BA equal to I. Both conditions are imposed in the definition, and in this case we say B is n inverse. So we are saying that A has an inverse if there is a matrix which satisfies these two equations. Okay. Later on, we will see that the inverse is uniquely determined. Moreover, if I prove AB equal to identity, it is enough. It will automatically imply that BA is also identity. So we'll prove both the things. Yeah. Let's look at this matrix A, which is a diagonal matrix, and prove that it is invertible. So we need to pull out another matrix so that when you multiply A with that matrix, you get identity matrix. Now remember, if I have two diagonal matrices, then I can multiply these two diagonal matrices simply by multiplying the diagonal entries. So look at this matrix B. Okay, there are and take the inverses of these diagonal entries. Okay, then I get this B, and you can check that A times B is identity and B times A is also identity. But on the other hand, if I look at this non-zero matrix A, whose rows are 1, 0, and 0, 0, this is not an invertible matrix. Okay, this is not an invertible matrix. Let us see why this is so. So suppose this suppose A equal to 1, 0, 0, 0 is invertible. Okay, it's an invertible matrix. That means, so then A, there is a matrix B, so that AB equal to BA equal to identity matrix. Okay. Now I look at the second basis vector, namely 0, 1. Okay, and then multiply A with E2. That is the second column of A. Okay. So therefore, BA E2 is equal to B times the 0 vector, and that is the 0 column vector. So BA operating on E2 produces the 0 vector. Okay. BA is identity. BA is identity matrix, and therefore identity matrix times E2. This is the second column vector of identity matrix, and that is 0, 1. Okay. So this is a contradiction, and therefore A is not invertible. Let's prove that inverse of invertible matrix is unique. So suppose C and B are inverses of A. Let us say there are two inverses of A. Then AC is identity, and BA is also identity by definition. Okay. So therefore, I can write C equal to identity times C, but I is equal to BA. This BA is equal to I times C. I use associativity, B times AC, but this AC matrix is identity because C is the inverse of A. And so therefore I get B times I, which is B, and therefore C equal to B. So the inverse of a matrix is uniquely determined. Yeah. So once the inverse is uniquely determined, we can have a notation, and we will write A to the power minus 1 as inverse of the given matrix. Let's talk about inverse of AB and A transpose. Okay. So we want to understand if I take two invertible matrices, whether the product is invertible. And suppose I know that product is invertible. Can I say the factors are invertible? Yeah. Suppose A is invertible, I take a transpose. Can I say A transpose is invertible? If it is invertible, what is its inverse? So this proposition answers both these questions. So suppose A is a square matrix, then A is invertible if and only if A transpose is also invertible. And in that case, A transpose inverse is A inverse transpose. Okay. Now, one consequence of this is that if A transpose is A, which means it is a symmetric matrix, then A inverse, A inverse will also be symmetric, because this is equal to A transpose inverse, and A transpose is A, so it is equal to this. So the inverse of an invertible symmetric matrix is also symmetric. Okay. Inverse of a symmetric invertible matrix is also symmetric. Okay. Suppose A is invertible and B is its inverse. Then we know that AB equal to identity equal to BA. Now simply take the transpose on both the sides. So I get B transpose A transpose is identity is equal to A transpose B transpose. And this implies that B transpose is equal to A transpose inverse. Okay. But we know that B is the inverse of A. So that implies what we want to prove. Okay. Therefore, A transpose is invertible, and inverse of A transpose is transpose of A inverse. So the operation of taking inverse and transpose, they commute with each other. Whether you first take transpose and then take the inverse, if it is invertible, the answer is the same as by first taking the inverse and then taking the transpose. Okay. Next, if A transpose is invertible, then we know that A equal to double transpose of A, and therefore by previous case, this is also invertible because transpose of invertible matrix is invertible. Okay. So therefore we have proved that A is invertible if and only if the transpose is also invertible, and this is the relation between the inverse of transpose and transpose of the inverse. They are equal. Okay. Now suppose A and B are square matrices. If A and B are invertible, then AB is invertible, and AB inverse is equal to B inverse A inverse. Okay. So our assumption is that A and B are invertible. We want to prove that AB is invertible. In order to prove some matrix is invertible, it's enough to say what is its inverse. So we are saying that the inverse of AB is B inverse times A inverse. So keep in mind that the order is reversed. AB to the power minus 1 is B inverse A inverse. Okay. Here is the proof. Suppose A and B are invertible, then we just multiply B inverse A inverse with AB, use associativity, and this gives me B inverse B, which is identity, and therefore B inverse A inverse times AB is identity, to prove that AB is invertible, I must also prove the second equation, that AB times B inverse A inverse is identity. But again, use associativity, so I can club B inverse, and I get A B inverse A inverse, and this is A inverse, and this is identity. So that shows that if A and B are invertible, then AB is invertible, and its inverse is equal. Try to understand what are the building blocks of invertible matrices. Okay, so we know a criterion when a matrix is invertible. What is the inverse of A times B, or what is the inverse of A transpose? But we want to now understand how to obtain invertible matrices. Yeah? What are the components? What are the building blocks of invertible matrices? Okay, identity matrix is invertible. That is clear because it's the inverse of identity matrix is identity matrix itself. So we want to now, I want to give you some simple examples of invertible matrices. These are called elementary matrices, and we will see that all invertible matrices are composed of elementary matrices, in the sense that any invertible matrix is a product of finitely many elementary matrices. Okay. This is if and only if criterion. It's a necessary sufficient condition that a matrix is invertible if and only if it is a product of elementary matrices. Okay. So in this sense, elementary matrices are building blocks of all invertible matrices. Okay. That's what we want to understand now. So what is an elementary matrix? So an elementary matrix is a matrix obtained from identity matrix by an elementary row operation. There are three types of elementary row operations I introduced. So apply those three elementary row operations to an identity matrix, and we get three types of elementary matrices. So what were the elementary row operation? You can exchange two rows. That is one. Then you can multiply a row by a non-zero number. That is another elementary row operation. Then the third operation was you can multiply a row by a non-zero number and add to another row. Okay, so if you perform these three operations on identity matrix, you will get three types of elementary matrices. So let's look at what they look like. So the matrix obtained from identity matrix by interchanging ith and jth row is called elementary matrix of type 1, and it is like this. So there are two rows here. Yeah. So we started with identity matrix, but we interchange ith row with jth row, and here I'm saying I is less than j, right? So the ith row is transposed to it is exchanged with the jth row. Then I get this matrix Tij. T for transposition. We are interchanging the ith row with jth row. This is called a transposition, and so we denote this matrix by Tij. That is the first type of elementary matrix. Yeah, this is an invertible matrix. Okay, this is an invertible matrix. So in order to see why this is invertible matrix, let me just look at an example. So we understand matrices by their action.